We are going to talk about some logarithmic story problems, and logarithms are used in a couple areas that are quite common. And um, logarithms are useful when you're looking at information that has a huge variability, like earthquakes. In earthquakes, you have massive earthquakes, and then you have little tiny earthquakes. And if you rated earthquakes on a linear scale, the numbers would be so different that it just wouldn't make sense. The little earthquakes we have around here might be given a number of like 500. And then the massive earthquakes that happen might be given a number like 12 billion. And the difference between 500 and 12 billion is so huge that we've decided to rate them on a logarithm scale. So instead of saying here's 12 billion and this is how much energy is in an earthquake, um, instead of instead of saying energy and then rating, so we could rate them, we say, okay, a 12 billion earthquake gets a rating of 12 billion. But not very many earthquakes happen around here. Most of them happen like right here, like at 8 or 300 or 250. Right? There are a lot of earthquakes here, and there aren't very many strong ones, but the strong ones are so strong that instead of making it a linear scale, we make it a logarithmic scale, which looks more like this. So we say this has 12 billion units of energy, and that one rates at a 6. And this one has 7 billion units of energy, and it rates at a 6.5. And 5.5, yeah. And then this one rates at 3 billion units of energy, and it rates at a 5, or something like that. So the difference between a 1 earthquake, well, 1 doesn't really, 1 is really nothing. So the difference between a 2 and a 3 might only be a small amount of energy. But the difference between an 8 and a 9 is a huge amount of energy. Okay, so it doesn't take as much power to go from 2 to 3 as it does to go from 8 to 9. And that's what logarithms do. No, I don't think so. Because hurricanes don't really get that high. The winds in a hurricane might reach 180, maybe 200. So there's not a big variability in hurricanes or tornadoes, but sound and earthquakes, they are rated on a logarithmic scale because the variability is just huge. So sound is the same way, decibels. Um, so if you're talking, normal voice might be like 60 decibels. And if you want to go up to 61 decibels, you have to double, essentially, how much energy you put into that sound. So the difference between a 60 and a 61 is much smaller than the difference between a 100 and a 101. Okay? That curve, it takes more energy to get up higher. So what I'm saying is, if the curve looks something like this, but we ignore all of that stuff. So if I wanted to go from a 1 or a 2 to a 3, I only need to use that much energy, right? But if I want to go between a 5 and a 6, then I need to increase this much energy. Does that make sense? So logarithms allow us to take huge numbers and shrink them down so we can compare them with small numbers. And the two biggest areas are earthquakes and decibels. So those are the problems we're going to work on today. The decibel formula, which is on page 371, is the decibel rating, D, is equal to 10 log of I over I sub t. And I sub t is a constant equal to 1 times 10 to the negative 12. Okay, flip over to 366. So that tan box in 366, the decibel is defined as 10 log of I over I sub t, where d is the decibel level, I is the intensity of the sound measured in watts, that's how much energy the sound has, per square meter, and I sub t is the intensity threshold of the least audible sound a human can hear. The human average threshold is 1 times 10 to the negative 12. Okay, now that didn't make a lot of sense to you. What's that? Oh, I'll show you. Okay. Yeah, watts per square meter. So let me lock this. So what they've done is they have identified the softest sound humans can hear. Okay, so there is a decibel level out, well, not a decibel level, but there is an amount of energy, and if you make a sound using that energy, it's not loud enough for us to hear, even if it's right next to your ear. Okay, and how much energy is that? Well, it's 1 times 10 to the negative 12, and it says W over m squared. That's watts, which is energy, per square meter. Okay, so what is that number? It's a really small number. It's 0.11 zeros and a 1. Okay? And if you use that much energy, which is a tiny amount, you can create a sound that the average human can hear, but they can't hear anything quieter than that. Okay? So that number is sort of the constant that goes into the equation. So we're going to take a sound and we're going to divide it by, we're going to take an energy and divide it by the least energy that produces sounds we can hear. This is not frequency, it's energy. So you would probably have to play with the frequency. I mean, if you were to put this much energy into a long wavelength, you probably wouldn't, or you probably would be able to hear it. Or no, you probably wouldn't be able to hear it because it would be too quiet. It would probably be a really high frequency. But actually frequency doesn't even apply to this. This is independent of frequency. Okay, so look on example 9 in 366. Suppose you have seats to a concert given by your favorite musical artist. Calculate the approximate decibel level associated with the typical sound intensity given by I equals 1 times 10 to the negative 2. So you're sitting in a concert and you're measuring decibel levels. That's how much energy hits you. And that energy is 1 times 10 to the negative 2. And we're just going to say 1e negative 2. And that is I. So we're going to put it in here. And I get 10 log of 1e negative 2 divided by 1e negative 12. Yep. This is I sub t. This number will go in the denominator every single time. So to type that in, we just do 10 log of 1, and there's an EE button. And I've forgotten where it is. Right above the comma. See how it says EE? Second EE, negative 2. And actually, you need to put that in parentheses. Yeah. But it just comes up as E. So 1 EE, negative 2, and then divided by 1 EE, oop, wrong button, negative 12. And you have to put it in like that. So each scientific notation gets its own parentheses, and then the entire thing gets its own parentheses. So we ended up with negative 12. Don't put minus. It's got to be negative. So that would be a decibel of 10. Now, decibels are really strange. What base are we working in? Base 10. So actually, to go from 60 on the decibel scale to 61 on the decibel scale, how much energy do you need? 10 times as much. And to go from 60 to 62, how much energy do you need? Not 20. It's 100 times as much. No, 100 is the decibel, but we're in log base 10, right? It's the log, which is log base 10. So if you are speaking at 60 decibels and it's not loud enough and you want to go up to 64 decibels, how much more energy does that take? 10 to the fourth. It takes 10,000 times more energy to go. No, each step is 10. So it'd be 10 times 10 times 10 times 10, which is 10,000. Right, it's exponential. And when you deal with an exponential graph, it grows so fast that you can't fit it on your paper. Right? You can only see a small amount of it. So to bring those high numbers down, we use logarithms. So logarithms allow us to tame exponential values because they grow so fast that it doesn't work. Well, if this is the quietest sound we can hear, and that was at whatever decibel that is, how do we get to here? Well, that's 10 to the 10. Right? Which is a huge number, 10 to the 10th. Yeah, so if we do 10 raised to the 10th, it's not going to fit on our calculator, 1e10. So that would be hundreds, yeah, so it would be 10 billion. It's 10 billion times stronger. Yikes. That's a lot. Okay. Okay, so the next one, your turn. See, we're up on page 367. Calculate the approximate decibel associated with 1 times 10 to the fourth. So I would just redo this equation. Not that one, this one. And I would replace the negative 2 with positive 4. Well, I'm on the top of page 367. Your turn in green. Yeah. Okay, so 160. That's a decibel level of 160. Yeah. And actually, I kind of lied to you a little bit about each step is 10. It's actually a little bit less than that, but it's not important. That's not going to change how we do problems. Okay, so look on page 371. So from 85 to 88, you're going to do the decibel one. Okay, so 85, you just plug in 10 to the negative 6, piece of cake. 87, you plug in 10 to the negative 0.3, piece of cake. All right? Yeah. And now for the next one, we have the Richter scale for earthquakes. And we get a new formula. And the formula is the magnitude of an earthquake is equal to 2/3 times the log of E divided by an E sub 0. In England, they say for 0, they say the word not. N-A-U-G-H-T, not. Like, it does not exist, kind of. So E sub 0 is referred to as E naught. It's just easier to say. So E divided by E naught. And E naught is a defined term. E sub 0 is equal to 10 to the 4.4. Yes. Okay, and the same basic idea applies. So if you go back to 367, the magnitude of an earthquake is measured using the Richter scale. So magnitude is the number that you get. It was a 7.3. It was an 8.2. Okay? Where E is the seismic energy released by the earthquake, and E naught is the energy released by a reference earthquake. E naught is 10 to the 4.4. Mm-hmm. Decibel is sound. Yep. So decibel is how loud sound is, and then Richter scale is how powerful was an earthquake. All right. So calculating the magnitude, same basic idea. If you know what E is, you just plug it in. So the example on page 367 tells us the energy is 1.1210, or sorry, e to the 15, which is a huge amount of energy, right? 15 decimal or 15 numbers before the decimal. That's massive. So we would type in 2/3 log of, and we need a, you didn't need that first one. So 2/3 log, and you need two sets of parentheses here because you have to do 1.12 e. Oh, I put 3. Sorry, you don't need 3. You only need 2. Let me get rid of that one. No, well, it won't, but I don't want to confuse anybody. Okay, e to the 15th, and then close the parenthesis, divide, open parentheses, 10 raised to the 4.4, and then close the parenthesis, and then close the other one. Like that. Yeah, it's a lot. So that would be an earthquake of 7.1. Okay? Now, to bump up to go from a 7.1 to an 8.1 takes a huge amount of energy, an unbelievable amount of energy. So when you hear, oh, I sat through a 7.1 earthquake, that's that's very powerful. But if you sit through an 8.1, that's much more powerful. Not just a little bit, but a huge amount, because that logarithm curve, like I showed you, here like a 5. There, 4s and 5s don't really damage anything. There's no damage. You can have a 6 and still the buildings are all fine. So if this is your logarithm scale, okay, and this is a 7.1, or sorry, if this is a 7.1 and I want to bump up to an 8.1, how far out there would I have to go? A long ways. And so this might be the energy required to get to 7.1, but the distance from here to the next one is even longer. Okay, so back to your assignment. So 89 you can plug in 10 to the 17th. 91 you can plug in. On 91 it's just 2 times 10 to the 14th. Nope. Nope. That's just kind of information. Okay. And then 93 to 81, you have a new formula. Or 93 to, sorry, 98. You have a different formula. And the formula is pH is equal to negative log base 10 of H plus. Well, it'll tell you in the, right, in there, it will just tell you what you need to plug in. So to go from a 7 to an 8 in pH takes a lot of what are they called, hydroxides? But to go from an 8 to a 9 takes a lot more hydroxides. And to go from a 7 to a 6 takes a lot of, Uh-huh. It is. That's how much acid or base is in something. So to go from a 7 to a 6, you need a lot of acid. You need a certain amount of acid. To go from a 6 to a 5, you need a lot more. So the further away you get from the middle, the harder and harder it is to get to those numbers. Okay? So your assignment is, and these are all just kind of plug and chug problems. We'll get to problems where we actually solve later. So you need to do 85 to, let me double check. It says 101. I want to make sure that's right. What page are we on? 371? Oh yeah, so 101 just has a new formula and 99 has a new formula. But basically you're just plugging numbers in and pushing enter. And then we'll work with solving later. So the assignment is 371. What was it? 85 to 101 odd. Good luck.